How can a search engine return results which are barely relevant to the query? Likewise, how can it omit results which seem to contain exactly the information requested? In semantic matching, climbing the tree for correct and relevant query results, we address this problem and suggest a solution. Born to serve an almost encyclopedic role, the Internet has historically been a source of data. Currently, Internet usage has been expanded to include all forms of both usage, data stored, and users at all levels of technological know-how. In addition, the amount of data and usage related to the Internet has exponentially exploded in the past few decades. We are familiar with the problem. Searching the web is like searching a huge, unindexed, single-column relation. Using text match ignores other forms of data, and searching for answers or specific information often takes longer than seems necessary. How can we improve the accuracy? Our paper suggests a novel matching algorithm which basically searches based on semantic meaning instead of just text display, and tangentially also presents a treatment of the concept of interpreting the intent of the query based on the semantic implications of both the queries and the pages. So let's look at an introduction to our solution and then go into the solution details. And to demonstrate those details, let's go through an in-depth example and then do a quick review of the relevant algorithms, an evaluation of our system and some lessons we've learned. We'll discuss some future work and then move on to a demonstration of our search engine. So words, we know, are more than a collection of characters. A word is an idea and a place in a structure. So for example, the word red. So as a word, it can just be a collection of character. It's over here we have in disjunctive normal form. We have R, lowercase or capital case R appended to lowercase or capital case E appended to lowercase or capital D. That's what it is as a word. But as an idea, we can't describe it. It's just a color. You can't describe a color to somebody who hasn't seen it. It's an idea. And in addition, we note that it also has a semantic meaning. For example, it is a color. It's related to other colors. It is a visual property. Now, we know that a machine can interpret text. We know that it can't interpret an idea. But what about semantics? We say that a machine can calculate semantics, as work has already been done to calculate semantic values of a word, and we want to rank pages with respect to both the semantical and the text value proximity. So our basic solution is to return each page based on its ranking, which will be related to the query by a semantic matching value, which we'll move on to define more specifically. So here's how we propose to do it. We'd construct a weighted tree for the query, which would be based on the semantics of the word. Every word in the query would be a leaf node in the tree, and each leaf node will have as parents all the other words which fall into the same category as the word on the leaf node. We'll go into some examples. Then each of these words will have as parent the category it falls into, and this pattern will continue until the root node object, the category to which all words belong. The tree will be weighted, with each subsequently ascending level having a higher weight and incurring thus a greater penalty on the matching word, which we'll see in the next slide a bit more details on. So here's a query tree. We have, if the query would be the word red, we have that at the lowest level, and as parents there are other colors, and the parent of those is the property color, and that moves up to this is a little bit of a condensed tree, up to the root node object. So we'll have each page represented by a similar tree, and every tree from a page will match the query tree at some level. And then each word on the page will earn the weight of the node that it matches to. So we'll incur a penalty. We mentioned the weight of a node level, so each word on the page will incur a penalty of the weight of the node that it matches to. And we'll call the TMW, the total matching weight, the cumulative value of all the weights earned by all its words, and then return pages ranked by TMW ascending. So a page with a TMW value of 0 will be an exact match. So here's an example matching SMVs. If we have the word blue on a web page and it matches at level 1, it will incur the weight of level 1. So the way it would work is that a query entered into a search engine will be sent to the semantic tree engine to be parsed into the tree. The STE will send that constructed tree to the semantic search engine. The semantic search engine fetches web page trees from a repository, and a TMW is determined in that semantic search engine for each page, and then page results are returned in order of TMW ascending. So here we have a search engine. Now this is Google, but we've built our own little UI for that, and we send it to that semantic search engine, which outputs that weighted tree. And over here we have the query tree sent to the SSE, and that's where the things occur. The SSE grabs web pages from the web page repository, and TMWs are compared in the semantic search engine to find the SMV, and their page results are returned. So let's go through an example. Step 1 is that the user enters a query. So we have the user entering the query, red Honda car. Step 2 is that our query is sent from the search engine, whatever that may be, over to the semantic tree engine. There in the semantic tree engine, a query tree is built. So we have here an example query tree, and the leaf nodes are red, Honda, and car, and the subtrees are in different colors for each, and let's zoom into each. So the one for red is at weight level 1, and it has as parents blue, green, pink, and of course it could have many other colors. And the parents of those nodes is color, the parents of that node is texture, shape, and size, and the parents of those nodes are visual property, and of course this continues up to object. We have here a similar subtree for Honda. Nissan, Toyota, BMW, there are the car brands, make, model, years, car price factors, and we have for car, van, SUV, sedan, types of car, models, makes, mileage, features, etc. So in step 4, the semantic search engine gets that tree. So it gets that tree, and what does it do? It fetches pages from the web page repository, and so these web page trees are sent to the semantic search engine, and here is where the calculation occurs. So this is a bit of a complicated slide, but basically it's a sample web page where words from the web page are calculated into trees, and the tree is matched with our query at some level. And each one incurs a weight based on the level that it hits, and this web page earns a cumulative weight of 4,368. And so here are the cumulative weights for some pages. Over there to the left is our UI. And it gets the highest page is actually a red Honda car, which only had a cumulative weight of 22, and the most unrelated page had a cumulative weight of 8878. Of course, these are just 5 sample pages. So here's just a quick overview of the algorithm for our tree construction, where we add the leaves and we build the tree. Here's how we assign nodes, and this it can be calculated to take minimal polynomial time to assign the weights. Here's how we match the SMVs, and just to note quickly that weights are ranked in ascending order, and that text matching is favored over semantic matching. Though semantic matching is factored in, text matching is ultimately favored. We have so just as our evaluation, which we'll see a bit more in the demo, we see that short queries overall perform better than long queries. We've also seen that it's hard to evaluate it properly, as our search is a bit limited because we had to work with an index portion of the database. We'll see that more in the demonstration. And overall, our search engine does return relevant results and demonstrates that accurate matching and relevance of semantic value is important for good results. Our search engine returns only up to 100 relevant values, and the result set includes the semantic value for each result. Some issues that we've stumbled upon are that we're limited by WordNet's ontology because we've used that to build our trees. We're also limited by the need for a custom index database. So far, our work cannot be scaled to an unindexed database such as the web, which is what we were aiming for, but we see maybe that we may not be able to do that. Another issue that we've come across is the performance. We take double time to search because we first have the time to index the database, and then there are some bugs which require double indexing time. We see that the trees that we've built may contain some duplicate layers, which exacerbates the performance issues. And we have a bit of a distance problem, which I'll explain in a bit later. But we did learn a lot of lessons. We learned that building a search engine is not easy. We learned that within a manually built search engine and a lot of the research work that the tools that have been built, there is that implicit reliance on a custom index database. We learned that performance is very important to make something work. We've learned that using dependencies may seem necessary at times, but they will end up imposing a lot of limitations on the solution. We've learned that time is very, very important, and that maybe this semester wasn't enough time to build a proper search engine. But one major thing that we've learned is that we may have a good solution, but it might not demonstrate perfect results. And yet it can still contribute a lot by introducing and elaborating on valuable concepts and teaching about and exploring the problem domain. So as future work, we want to analyze and perhaps improve performance. We want to find a way to evaluate results more automatically. Now we're doing it pretty manually. We want to explore ways to compact our output trees. And we want to work on the distance problem, which I mentioned earlier, and basically refers to the fact that if the word red comes up far from the word car, it shouldn't have the same value as a page that has red and car close together. So now let's move on to look at a demonstration in part 2. Thank you.